you can say what is happening here. Look here. I mean, we have different, you can say S1, S2. I mean, you can say the signals that are you can say being generated. They are being summed up, and when they are transmitted, I mean, the noise comes into picture in the channel, and then at the other side, you provide this particular UVG code, and then you integrate it, and then you detect like MJTM. I mean, for the JH user, what I'm integrating is from 0 to TM for a, you can say, corresponding to one, time duration. So MJTM, what is MJTM? That's the voltage at the, you can say, integrated and dump circuit at the decision instant. So that's my output, you can say MJ. And this is MJ is, this is my signal voltage. But what does this, this voltage consist of? This is the signal voltage. And then along with the signal voltage, I have a, you can say, ISIN noise voltages also. Because when you correlate, as I said earlier on also, when you correlate a particular, signal with its own, you can say, code, there will be, you can say, it's a, signal that we are looking for. Along with that, whatever the correlation that is being generated with the noise and other, you can say, signals. So this particular, term represents your signal voltage, and this particular term represents ISIN noise voltage. I mean, correlated. You can say it may be interference or some other things also. So the jth user experience is the signal to, I mean, how much signal to noise ratio for the jth user. Jth means, I mean, there will be obviously number of subscribers as we are talking in case of CDMA. And so for the jth user, the signal to noise ratio calculation we can say is what signal power is, means what, MJJ. That's what the signal power we will display, because that's what the intended power we are looking for. And along with that, what we have is, you can say, this expected value or the mean value, you can call it in a way, of this interference and noise signal. I think that's fairly, straightforward. Okay. And if you do this, this EMG plus NG calculations, if you square it up, one term we will have corresponding to this MGI, another one will be twice of E. I mean, that's as simple as x plus y all square is equal to x square plus y square is equal to plus 2xy. So that sort of, relationship here. And this is expected value for channel noise. This is my MAI, understand? Multi-axis interference. What is the meaning of multi-axis interference? The meaning of multi-axis interference means, that means the code that we are using, I mean, they may not be, you can say, be perfect. So they cross correlation output also, you can say, will be finite. And this excess interference, because, as I said, near far problems also, because a lot of subscribers are, you can say, trying to get access. And in that case, someone is transmitting more power, someone is transmitting less power. So that also generates some sort of, you can say, interference for the other users. You understand, students? I mean, is this, I mean, very, very straightforward, you can say. I mean, you are having your intended, you can say, signal, along with you have, you can say, different signals, which, which we can name as multi-axis interference, and the channel noise mainly, and of course, the combination of the two. That's, I think, very straightforward. Okay. Now, let's say in a practical CDMA receiver, what we have a, let's say, channel, low pass channel, then the local code, we multiply it, and then this integrator, and then there we make a decision. Decision means whether 1 or 0 has come, phasing of sampling, you can say. Now, that's obviously, I mean, you can say, what is LC? By, you can say, chips, I mean, length, PJ. This is WPJ upon R. I mean, I can write my, you can say, chips corresponding to in a spread across as WPI, this thing. So that's my, you can say, what is my corresponding MJJ is the signal I'm looking for, you can say. And this signal, this gives me my, you can say, my PI. PI means what? I mean, the signal I am looking for, intended user. And this gives me my PN. That means, let's say, noise. This is N0. B effective. B effective means, I mean, effective bandwidth, you can say, corresponding. What will be the noise corresponding? Okay. So what is effective bandwidth? Effective bandwidth, understand meaning of effective bandwidth essentially is 0 to infinity VF DF upon VF DF1. Okay. So that means it's taking account all of, you can say, the signals, you can say. So for rectangular spectra, this VF is what? VF, you can say, if it's a rectangular pulse here. Now this is my, you can say, bandwidth BN. and this is, you can say, x-axis frequency, and here I'm, let's say, plotting voltage as a function of frequency. So that's a fairly, let's say this kind of, pulse I have across the frequency domain. So my B effective will be Bn S0 square upon whole square upon Bn S0 square. So this term I can define as, you can say, as Bn. Okay, understand? I think uh, maybe initially little bit of, you can say, you are not at least very uh, familiar, but you can it's a straightforward. I mean, I'm trying to calculate, you can say, my B effective, which I am defining as N0 B effective, means of what is meaning of this B effective here. And what does it mean? It says SNR upper bound for the jth user. Okay, what is upper bound? That means how much voltage I'll generate, you can say, corresponding. Okay, for the jth user I can write as upper bound, this should be less than equal to LCPJ. That's LC is what, my chip length, I mean the PN sequence, you can say, code, and corresponding to PJ, that's my signal I'm looking for, and this is my, again, this corresponding to this denominator term. So upper bound means, I mean, I'm looking for how much power, you can say, it should be across. Now, what is meaning perfect power control? As I said, equal receipt power for U user means, that means all the users receive the equal power, because someone user is nearby, obviously he should get less power than the user who is, located far away from the base station, or from the any, you can say, wireless, you can say, service or transmitter. So if you look at, if I say equal receipt power for you other means, that means what? I mean, I sum up all the, let's say, power Pi, let's say, and what does it mean? It means essentially how many, you can say, U minus 1 Pj, how many users are there. So one user, let's say, myself or anyone else, I mean, who is his intended subscriber, and what others are doing, you can say, others are also contributing this kind of, you can say, power to the signal. Therefore the jth user SNR equals, that is equal to N0BF U minus 1 PJ. Understand? Because that's a multi-axis interference, you can say. This is my noise, and this is my LCPJ. That's, I mean, you can say, intended signal I am looking for. And the number of users, as I said again, U, I mean, I can calculate this. These users are related with that. Now for BPSK, this is corresponding to, I can define this relation LC, that corresponding, I mean, LC essentially, maybe you can, we can call it a processing gain also, but it is, you can say, corresponding processing gain means essentially how much expansion has taken place. That means what is the, you can say, the bandwidth occupied by the chip, and what is the, you can say, corresponding, you can say, bandwidth occupied by my baseband. So how much expansion has taken place, that represents my LC, let's say, in this notation. So channel, I'm presuming N0 level, I mean AWGN, processing gain as LC, and received power as PR. Okay. So if I do calculation for assuming it to BPSK modulation, you can see my signal to noise ratio ultimately turns out to be 2 EB upon N0. 2 EB, we have done so many times calculations, and then we know it also that the bit error rate is essentially, you can say, depends upon EB upon N0. What is plotted here is AWGN level decreases, let us say. I mean, that means my white noise power, that's a decreasing. And if you look at my U maximum, okay, so how much power I can generate corresponding to. Look here, this is my processing gain, this is signal to noise ratio. So this U maximum, that means how many subscriber, you can work on corresponding to. So this is, you can say, received signal to noise ratio without multiple access interference. I mean, this SNR1. Understand? This little bit, maybe it's, you are already studying it first time, but if you read it again, probably you will get a better idea, or better, conceptual, you can say, why we need a multi-user detection system. Unequal receipt powers, near far effect. This is a, you can say, contrast to the earlier case where I say that all the subscriber are getting, equal power. Here I say it's a unequal receipt power. So I assume all users apply the same power, but their distance to the receiving node is different. Hence, the power from the ith node is, obviously, it will be depending upon my distance di, where d is the distance and alpha is the propagation attenuation coefficient. I mean, how much power, maybe d square, maybe d 2.5, or whatever the corresponding relationship that holds on corresponding to. So alpha is equal to, for free space, normally it is presumed. In urban area, alpha may be 3 to 5 also. And then express the power ratio of the ith and jth user at the common reception point. Okay. So common reception point, maybe you can say the base station, let's say. So how much, power P0, that is Pi Di. If I, add up, you can say by jth and ith user, I can write as Pj dj alpha. I mean, if they are, corresponding to at a common reception point. So this Pi becomes Pj dj upon Di. I mean, obviously in the ratio of distance, that particular power, you can say, will be calculated. Therefore, the SNR of the jth user. So jth user SNR will be my LCPG upon N0 by B effective upon I is equal to 1 for all. I mean, I is equal to J, I is equal to corresponding, I1, and summed over all users, you can say, my PIs. So signal to noise ratio will be less than for the jth user will be. No, look, this calculation is about, you can say, earlier on we saw that all powers are transmitted by subscribers are same. Here the power transmitted are different. So that calculation is unequal receipt power at some common point. Now I have already explained you near far effect. In asynchronous CDMA, what does it mean? Grouping the previous yield condition, I can define this as, this ratio as, it turns out to be, if I simplify it further, this may be U minus 1. So what does it mean? It means essentially multiple access interference power should not be larger than what the receiver sensitivity can accommodate. Okay. So that means I have to somehow reduce multi-access interference power. And multi-access interference power, you can say interference is obviously directly, you can say, related to, you can say, the kind of interference generated by the other users for the intended user. Understand? It should not be larger than the received sensitivity. What does it mean? That means the receiver can handle it or cannot handle. And remember, we are dealing with a system which are very low power, systems. So this interference is, little bit of interference may be also problematic. Note that the manifestation of near far effect, because just one larger sum term on the left side of the equation voids it. Now, even a single, you can say, user may be problematic. Assume that all हाँ लाओ हेलो हाँ मैं लेक्चर में हूँ लाओ अभी हैं हाँ हाँ 12 बजे फ्री हो जाऊंगा हाँ. So the near far effect in asynchronous CDMA. So if you look at DJ upon DI ratio, that's a less than equal to LCMI processing gain 1 upon SNR 0 minus 1 upon, that we have. And the example you can presume here is, assume that all but one transmitter have the same distance to the receiving node. The one transmitter has the distance D1 as DJ upon 2.5 and alpha is 3.6. That is an example. I think numerically you can solve it. Okay. So what this particular numerical values give you corresponding to, if you look at this, your LC BPSK, LC means processing gain, that's about twice TB, B effective, and users, number of users you can as equal to 14, you can say. That can be, number can be handled. So basically this is a calculation to, for the near far case. Near far means essentially, I think the simplest thing you can visualize is any subscriber in a CDMA system, if it is, you can say, located very near to the base station, and if it's transmitting the same power that a subscriber is transmitting from a distance away, then obviously this will look at creating more interference for the distance user. So that we are calculation we are doing only, like, how many users for this kind of calculation for, and this d to the power means essentially, remember that now this is our, you can say, empirically, verified, you can say, relationships, so d1 is equal to dj upon 2.5, something like alpha is 3.68. That means the power that we are talking, dj upon d1 in the upper equation. By using the perfect power balance, the number of users, look here, if a single user is having more power, It only comes to 14 there. If you have a perfect power balance, then the users can be increased to a level of 42. So that's a difference. That's what the, you can say, perhaps we have to, it's a necessitated by that. You have to find a solution for this kind of, you can say, near far problems. Hence the presence of a single user so near has dropped the number of users into almost 1/3 part of the maximum number. In this, user comes close to the, you can say, corresponding, all the other users will be rejected. They cannot communicate in the system if required SNR level. Understand? I mean, the user who is away from this base station will not be even, and his call may not be entertained because of the interference of the by this fellow who is very near to the base station and transmitting so much power. To minimize the near far effect, efficient power control should be adaptively. I think that perhaps all of you know that. Now, fighting against multiple access interference, you might say that what is the solution for that, for near far or this multiple access interference? So in CDMA system can be realized by spreading code having low cross correlation, as gold codes asynchronous usage and Walls code synchronous usage. As I said earlier on, you do not have right now any background in coding, but these are the codes, you can say, called error control codes, which are used for, you can say, reducing the errors in the transmission. So gold code and Walls code, you can say. Now gold is corresponding to, you can use for asynchronous, while Walls code can be, you can say, for synchronous. And Walls code is mostly used in a CDMA system in the very beginning, you can say, and it is a block code about, you can say, where the message length is about 45 bit and you have 17 18 as parity bits, so it's about 63 bits, you can say, in total length. Multipath channel with large delay spread can destroy cross correlation properties. Understand? Multipath channel, because wireless is in any case multipath, so large delay spread can destroy cross correlation properties. What is the remedy? Asynchronous systems with large code gain assume other users to behave as Gaussian noise, as just analyze. So, I mean, uh, you can make use of asynchronous, at least system, rather than going for synchronous. Additional compensation of MAI yields further capacity. Compensation means essentially you negotiate or you try to reduce that or try to eliminate that MAI by, so that will increase the receiver sensitivity and obviously more subscriber can be accommodated. This can only be achieved by code waveform design. Okay, so what is meaning of this compensation of MAI? Code waveform design, that means bandwidth rate trade-off. Okay, how much bandwidth you want, how much speed you want, the trade of that, you can say. So code waveform design may be one solution. Power control, minimize the near far effect. Forward error control and ARQ, automatic repeat request systems, diversity systems, spatial frequency time, and multi-user detection. I mean, these are some of, you can see, the possible solutions. So again, the multi-access interference versus ISI, inter-symbol interference. Okay, you understand that. Note that there exists a strong parallelism between the problem of MAI and that of ISI. It's the same thing, you can say. ISI, one bit is overlapping with the other bit, and here also this particular problem may lead to, you can say, interference. Asynchronous channel of k users behave the same way as a single user channel having ISI with memory depth of k minus 1. So look at, I mean, if you have the same kind of, system response for k users, if a single user is suffering from a ISI depth of, you can say, memory depth of k minus 1, that's an order defined for corresponding, you can say, this ISI. Hence the number of multi-user detectors have their equalizer counterpart as, okay. uh, what is meaning of this, you can detectors? I mean, how do you negotiate this kind of ISI? So we negotiate it by, you can say, some, you can say, using equalizer counterparts such as maximum likelihood, zero forcing, minimum mean square, and decision feedback. These are some of, you can say, the compensation, you can say, or perhaps, reducing this symbol interference. General classification of multi-use detectors are, they may be linear, they may be subtractive. Maximum likelihood sequence detection, if you use that, and then optimum multi-user detection applies maximum likelihood principle. Okay, So what does it mean? Considering the whole received sequence, find the estimate for the received sequence that has the maximum distance to the allowed sequences. Understand? It's very simple. I mean, you can say whatever sequence you have received corresponding to, and then what you do is you estimate the received sequence based upon the fact that this has a maximum distance to the allowed sequences. I mean, maximum distance that is being generated. So the ML principle has the optimum performance provided transmitted symbols are equal likely. Okay, symbols, if they are equal likely, then this can give you optimum performance. Has large computational complexity in exhaustive search, 2nk vectors to be considered. Okay, so k users, n bits. I mean, this many of the search you will have to perhaps make out, and so it's very exhaustive. You can say there will be obviously delays. You can say requires estimation of received amplitude and phases that takes still more computational power, because you have to estimate, as I said earlier on, uh, in all these detection systems you have to estimate and then reach to the conclusion that probably that has been transmitted. Can be implemented by using Viterbi decoder, that is practically optimum maximum likelihood detection scheme. I think this is very advanced little bit, so maybe you, but I mean, when you will be doing some course in advanced digital communication, you come across this maximum likelihood detection scheme to reduce computational complexity for surviving path selections. We discuss first the conventional detector by following the approach we already you can say had to familiarize to denotions. So formulation means, I mean, received signals, si- single path AWGN channel, perfect carrier synchronization, BPSK modulation. That's a, I mean, we are presuming that, let us consider that case. Okay, so how the detection goes on. Received signal is therefore, what will be the received signal? Received signal is, you can say, your signal that is correlated with your sequence and to your baseband signal. Okay, plus NT. And where for k users, I mean, you have you can say I is equal to 1 to k users, akt is the amplitude. Okay, I mean, for different users you can define, you can say corresponding to ak as a different parameter, no problem. Gk is, gi is the spreading code waveform, you can understand. dkd is the data modulation of the kth user. Okay, that means the data, and nt is my noise. That's very straightforward, I think. Huh? Yes, students. And that there are LC chips per bit. Okay, I mean, that's a processing gain that we are providing, you can say corresponding to. But I think this equation RT, that means the signal that is getting generated is depending upon my, you can say, amplitude of for each user, my code, and my baseband data that I'm along with the noise. Now, conventional detection without MUD. If you have a conventional detection without multi-use detection, how does it look like? The conventional DS receiver for K user consists of K match filters. Okay, or correlators. Understand? Suppose this is my RT I'm getting. Then in a conventional without multi-user detection, what I'll do? You can say provide, you can say, corresponding to match filter for each, you can say, corresponding code. Okay, so that means, I mean, I have a XT here, X2, X3, X4, whatever the number of codes users are making use of, I'll correlate the incoming signal with that particular code. And then like G1, G2, G3, and the product of my incoming signal along with my code, that is fed to my, you can say, this match filter or correlative receiver. And then I make the decision that D1, D2, or which particular input has, or which particular user input has come. Each user is detected without considering background noise generated by the spreading codes of the other users to be deterministically assumed to be genuine. I mean, that's what the assumption we make. So this is detection uh, quality depends upon code, cross, and autocorrelation that we have already talked. The obviously detection will depend upon, I mean, my autocorrelation and cross correlation. Autocorrelation, you can say, corresponding, if it generates maximum, obviously that signal will be taken. I mean, cross correlation, if if some code are generating, then obviously that may be problematic for the system. Hence, we require a large autocorrelation and a small cross correlation. That's obvious, I think. The output of kth user consists of the signal, MAI, and filtered Gaussian noise process. Okay, so that's simply my signal, my multi-axis interference, and filtered Gaussian noise terms. You can say if I RT, if I correlate with my, you can say GK, that's my PN sequence or my code. And this kind of output you can say. So I generate, you can say my ADK DK here, and this is corresponding to my MAIK. I mean, you are essentially what you are doing is AIDI, and along with this particular matrix, depending upon the number of users, and this is my noise ZK. So received SNR of this was considered earlier. I mean, in the earlier lecture also. Like, so that's the matrix notation to consider detection for multiple access. Suppose three user synchronous system with match filter receiver. We have, let's say, three user, and each user y1, what is generating a1 d1, row 21 a2 d2, row 31 a3 d3 plus z1. Let's say only the three users are there. So I'm calculating that corresponding to y1, y2 is what you can say corresponding to row 1 2 a1 d1 a2 d2. I mean, that's a, you can say it's on signal a2 d2, this on signal a1 d1, and this a3 d3. All these signals are, you can say, cross correlation. Correlation means 2 1, 2 with 1, 3 1, 3 with 1, 1 with 2, and 3 with 2. So that these are generating some multi-axis interference terms, you can call them. So my y1, y2, y3, you can see this user input may be 1 1 1, because these particular terms should obviously generate maximum. You can say I can define them to be unity. Row 2 1, these are my cross correlation terms. And if I look at this particular matrix a1 a2 and a3 d1 d2 d3 z1 plus z3, that's a equation you can write very easily. That is expressed by the matrix vector notation y is equal to rad. What is r? That's a correlation between each pair of codes. Okay, correlation, like this one, correlation row 2 1 row 1 2. So this is a correlation between each pair of codes. A is received amplitudes, that's the amplitude received, because I am looking for a1 a2 a3, you can see corresponding components for the y1. Then z is my data. Okay, the data that I'm looking for, you can say corresponding to these three users, and z is my noise. The data term and the MAI term. The matrix R can be partitioned into two parts by setting y is equal to RAD plus Z, with R is equal to I plus Q. I can do that. I mean, in phase, or you can say if you are using, you can say PAM, QAM, or some other modulation. Note that hence Q contains of diagonal elements R or the cross correlation component, and therefore my MF output, that y is equal to RAD plus Z can be expressed as I plus Q A Z AD plus Z. Therefore, term AD contains the decoupled data, and QAD represents my MAI. So I have, you can say, I can again say that's my, I mean, data that I'm looking for, and that this particular another term, my, you can say QAD, that represents my multi-access interference. Objective of all multi-user schemes is to cancel out MAI. We have to somehow eliminate MAI as any multi-user detection scheme as effectively as possible, constrained to hardware software complexity and computational efficiency. Understand? Now, this is asynchronous and synchronous channels. In synchronous detection, decision can be made bit by bit. In asynchronous detection, bit overlap, and multi-user detection is based on taking all the bits into account. Okay, so if it's asynchronous, I have to take into account all the users. If it's a synchronous, I can take bit by bit. Okay, so like tau 1, I mean, if you corresponding to delays, you can calculate 3 TB plus T tau 1. So that means, I mean, by delays, you can say this is T1, T2, TB plus T1. This is asynchronous. My users are, you can say 135 or 246, whatever corresponding users we are using. So in synchronous detection, schemes can be made bit by bit, and asynchronous detection bits overlap. Like look here, 1 and 2 are overlapping. Okay, and multi-user detection is based on taking all the bits into account. I mean, they you can say joint. I mean, they detect combinedly. The matrix R contains now partial correlations that exist between every pair of the NK code words. Asynchronous channel, correlation matrix, if you look at asynchronous, depending upon what is in this example, the correlation matrix extends to 6 into 6 dimension. Okay, if you have a corresponding correlation, maybe rather than 3 users, it may be 6 users. Let us say if you take on, then R will be looking like that. You can say resulting matrix is sparse because most of the bits do not overlap. Okay, and sparse matrix algorithm can be utilized to reduce computational difficulty. That's then decorrelating detector, you already know. Decorrelating means what? You correlate the coming you with this sudden, you can say chord, and again it's the same concept, you can say auto correlation, because the user the incoming signal will generate zero output for, you can say, for a user which does not use that particular kind of code. Okay, so the decorrelating detector applies the inverse of the correlation matrix to suppress MAI. Obviously, you can say, I mean, if it is a, we calculate the corresponding matrix, then this decorrelator, this will, we will have to calculate the inverse of the correlation matrix to suppress MAI, and you can say corresponding R minus 1, and the data estimate is therefore, I can write R inverse Y. Okay, and the decorrelating detector, as I said in the very, I mean, when we were studying about detection, that this particular, you can say, batch filter and decorrelator, I mean, these are correlative receiver. These are the only two categories of receivers which are used for recovering, you can say, digital bit, transmitted bits. Decorrelating detector eliminates the MAI completely. However, channel noise is filtered by the inverse of the correlation matrix. This results into noise enhancement. Now try to understand what happens to the noise. Noise correlation means what? You can say your code gets correlated with the noise. What is the output? It may be, you can say, reduced also, it may be increased also. So that's what is being talked here. Okay, so the channel noise filtered by the inverse correlation matrix, this may result in noise enhancement also. Decorrelating detector is mathematically similar to zero forcing equalizer. We have already talked about zero forcing equalizer in one of our transmission of in a band limited channels earlier on lectures. Decorrelating properties. What are the properties of decorrelating? Provide substantial performance improvement over conventional detector under most conditions. Does not need received amplitude estimation. Has computational complexity substantially lower than the maximum likelihood detector. Linear with respect to number of users. Correspondence maximum likelihood detection when the energies of the user are not known at the receiver. Has probability of error dependence on the signal energies. Okay, these are the pros. Advantage. Cons are noise enhancement, high computational complexity. So this is, I think, let me stop here. We will do this thing, next one, you can say, corresponding polynomial expansion detector or all other remaining part in my next lecture tomorrow. Okay. Yes, students, any question you want to ask? I mean, don't, this is just for to give you an exposure about, multi-user detection. And it's in any case integral part of the CDMA systems, mostly used in CDMA systems. So that is to give you an idea about what the concept of multi-user technology is all about. So, I mean, you try to understand it if you can. It's very straightforward. I think so far the discussion, we have not used much of the mathematics, perhaps, which is beyond your understanding. It's a very simple, you can say. So far calculations are, even those are, you find somewhere difficulty, you can refer to the text, or I mean, I'm here in the lecture also. Tomorrow we will have some maybe tutorial also, some, and then this particular lecture also, maybe the last lecture, I think, probably as per your schedule, or we have some more lectures, students. Yes, please.
Sir, according to the schedule, we have classes till 28th of January.
28th, huh?
Yes, sir.
20th or 28th? 20th.
28.
28.
8.
Oh, then it's okay. We will have probably another week of, at least just 3-4 lectures, maybe. No problem. I think we will see that if there are any other topics available, we will do that, or maybe some, tutorials we can have. at least to give you some numerical problem solutions in the lecture classes also. No problem. Okay. And then I think each student should submit your, you submit please your this particular, you can say, assignment that I had given you earlier on. Okay. Okay. This is all for today.
Sir,
Yes. Any question?
sir, you have not shared the slides.
Oh yes, I'm probably I didn't find. I had another, some other busy schedule yesterday also, but today I hopefully I'll give you. I mean, whatever I have covered in the this particular online lectures. I think earlier lectures I had already given you or not, huh? Like line codes or others. I think I had already given you.
Sir, after midterm.
Okay, after midterm, no, no problem. I'll give.
And sir,
I'll
one more thing.
yeah.
Which chapters from the book are you covering? Uh,
This one is from I think multi-user. You will have to pick up some spread spectrum book.
Sir, after midterm, which books have you referred, sir,
I
so
had
that we
referred,
can...
yeah, I had referred. You can see top selling only for match filter and decorrelating receivers. Even the orbit error calculation also, I have only referred that book. And you can submit your assignment to my mail also. Okay, either combined form, or you can say as a group of 3 4 student or 2 student or six. Of course, ideally I would have liked at least one of your coordinator in the group, and then in you share some common, you can say, discussion among yourself, like this is what should be included, this is why it should be included. So I wish, I mean, let's like each one group, all students, they discuss together and then they prepare a report. Okay, if you have it's not possible right now, maybe online, so you can submit your individual also, no problem. Okay, is it clear? And this assignment will have some certain credit also. Remember that a student who does not submit, obviously he will not be given that credit.
So where
So
should we submit it?
you submit. If you are in the hostel, you can submit to my room, if you know my chamber official. If you are in the hostel, if you are at home, then submit, I mean, online through my mail. You can on my mail email address, you can submit that.
So it can be typed as well. You
Yeah,
said in the...
yeah, you can type also and scan it and then you can submit. Okay.
Okay.
Okay, and no problem in any form, if you whatever you are comfortable with, no problem.
So
Okay.
last date was 21. You said after
Yeah,
2 weeks.
I wanted to 21, but maybe you can take another 1 or 2 days, no problem. All I want is
Okay.
at least you learn something about out of it. Okay. Okay. Any other question, please? Okay.